Most people think the hardest part of hydrogen is making it. When people hear about the hydrogen economy, they usually imagine giant electrolyzers splitting water into hydrogen and oxygen, massive wind farms supplying renewable electricity, or futuristic trucks driving down the highway powered by hydrogen fuel cells. Yet hidden inside nearly every hydrogen station is a machine that receives almost no attention, despite being absolutely essential. If this machine disappears, the station stops working. The storage tanks remain largely empty, the trucks cannot fuel, the hydrogen economy grinds to a halt. Sitting quietly at the center of this station is the hydrogen compressor. It is the machine nobody notices, even though it makes everything else possible. Look at the station around it. On one side sits a hydrogen-powered truck waiting to be fueled. Nearby are high-pressure storage tanks designed to hold compressed hydrogen. The dispenser is visible. The storage vessels are visible. The truck is visible. Yet the compressor is the hidden piece connecting all of them together. Every kilogram of hydrogen flowing through this facility passes through the compressor before reaching storage or transportation systems. It performs one of the most important jobs in the entire hydrogen value chain, but most people have never heard of it. To understand why the compressor is so important, we first need to understand a fundamental challenge associated with hydrogen. Hydrogen contains an incredible amount of energy for its weight. 1 kilogram of hydrogen contains roughly the same energy as a gallon of gasoline. That sounds impressive, but hydrogen has another characteristic that creates a major engineering problem. It occupies an enormous amount of space. If hydrogen remains at relatively low pressure, storing useful quantities becomes difficult and expensive. Large amounts of hydrogen require huge volumes. This means storage systems become larger, transportation becomes more difficult, and infrastructure costs rise dramatically. This is why hydrogen must be compressed. Compression allows engineers to take a large volume of hydrogen and reduce it into a much smaller space. Imagine having 1 kilogram of hydrogen spread out inside a large transparent container. The volume is substantial. Now imagine compressing that same kilogram into a much smaller cylinder. The amount of hydrogen remains exactly the same, but the space required to store it decreases dramatically. This transformation is what makes hydrogen practical for real-world applications. Without compression, hydrogen fueling stations, transportation networks, and storage facilities would become impractical on a large scale. Hydrogen does not normally begin its journey at extremely high pressures. Depending on the production method, hydrogen may emerge from an electrolyzer at pressures around 20 to 30 bar. While that pressure is significant, it is nowhere near the pressures commonly required for transportation applications. Hydrogen vehicles often rely on storage pressures approaching 700 bar. That means the hydrogen must undergo an extraordinary pressure increase before it can be used effectively. Moving from 30 bar to 700 bar is not something that can simply happen instantly. Instead, hydrogen travels through a carefully engineered pressure journey. Think of the process as climbing a staircase rather than jumping to the top floor of a building. Hydrogen may begin at 30 bar before being compressed to around 100 bar. From there, it may move to 350 bar. Finally, it reaches approximately 700 bar. At each stage, the hydrogen molecules become more densely packed. The spacing between molecules decreases as pressure increases. The result is dramatically improved storage density. The higher the pressure, the more hydrogen can fit inside a given volume. This gradual increase in pressure forms the foundation of modern hydrogen infrastructure. Inside the compressor, this process becomes a remarkable example of engineering precision. Hydrogen enters the machine at relatively low pressure. It then passes through multiple compression stages. Pistons move back and forth inside specially designed chambers. Valves regulate the direction of hydrogen flow and prevent reverse movement. Each stage increases pressure before passing hydrogen to the next stage in the sequence. The flow paths are carefully designed to maximize efficiency and maintain control throughout the process. What appears from the outside to be a single machine is actually a collection of coordinated systems working together to transform low-pressure hydrogen into a high-pressure energy carrier. The challenge becomes much more complicated when we consider what happens during compression. Compressing a gas generates heat. This is one of the most fundamental principles of thermodynamics. As hydrogen molecules are forced closer together, temperature rises. The greater the pressure increase, the more heat is generated. Hydrogen entering the compressor may begin relatively cool, but as it progresses through successive compression stages, temperatures can increase significantly. By the time hydrogen reaches the final stages of compression, thermal management becomes one of the most important engineering challenges in the entire system. Heat affects everything. Excessive temperatures can reduce efficiency, accelerate wear, degrade seals, and shorten equipment life. High temperatures also increase operational challenges and can complicate safety management. Engineers cannot simply focus on generating pressure. They must simultaneously control temperature. In many ways, compression and cooling become two sides of the same engineering problem. Every increase in pressure must be accompanied by effective heat management. This is why cooling systems are integrated directly into hydrogen compression infrastructure. Heat exchangers absorb thermal energy from the compressor. Cooling water loops transport heat away from critical components. Pumps circulate coolant throughout the system. Radiators release heat into the surrounding environment. These cooling systems operate continuously while compression takes place. Their job is to ensure temperatures remain within acceptable operating limits while maintaining efficiency and protecting equipment. Many people assume the compressor's primary purpose is generating pressure, but cooling plays an equally important role. Without cooling, high-pressure hydrogen compression would become significantly more difficult. The cooling system allows the compressor to maintain performance while protecting materials and preserving long-term reliability. Every component inside the machine benefits from effective thermal management. The result is a system capable of operating under extreme conditions while maintaining stable performance. Temperature is only one challenge. Hydrogen introduces another problem that many people never consider. Hydrogen molecules are extraordinarily small. In fact, hydrogen is the smallest molecule in existence. That tiny size allows hydrogen to penetrate spaces that would easily contain many other gases. Seals that work perfectly in conventional industrial systems may not perform adequately when exposed to hydrogen. Materials that seem solid can gradually experience hydrogen penetration over time. Preventing leaks becomes a major engineering objective. Hydrogen molecules constantly seek pathways to escape. They move through microscopic gaps and exploit imperfections that would be insignificant in other applications. Engineers must therefore design hydrogen systems with extraordinary precision. Seal materials must be carefully selected. Component tolerances must be tightly controlled. Connections, valves, and fittings must be engineered specifically for hydrogen service. Every detail matters because even a tiny leak path can become significant over time. Another challenge emerges in the form of hydrogen embrittlement. Certain metals can experience changes in their mechanical properties when exposed to hydrogen. Hydrogen atoms can diffuse into the material structure and increase susceptibility to cracking or degradation. This effect becomes particularly important under high-pressure conditions where materials experience repeated stress cycles. Engineers therefore rely on specialized alloys capable of resisting hydrogen-induced damage. Material selection becomes a critical aspect of compressor design. Embrittlement-resistant alloys, advanced seal materials, specialized coatings, and precision engineering all contribute to preventing leaks and maintaining reliability. These solutions do not happen by accident. They result from decades of research, testing, and operational experience. Every material inside a hydrogen compressor has been selected for a reason. Every design choice reflects the unique challenges associated with high-pressure hydrogen service. Because hydrogen operates under demanding conditions, safety systems become absolutely essential. Modern compressors incorporate multiple layers of protection. Pressure sensors continuously monitor operating conditions throughout the machine. Temperature sensors track thermal performance across critical components. Leak detection systems search for signs of escaping hydrogen. Vibration monitoring systems identify abnormal mechanical behavior before problems become serious. Relief valves provide protection against overpressure events. Automated shutdown systems stand ready to secure the equipment if operating limits are exceeded. Together, these systems create a comprehensive safety architecture. Think of them as the nervous system of the compressor. They collect information continuously, analyze operating conditions, and respond when necessary. Modern control systems process enormous amounts of data every second. This allows operators to identify trends, detect abnormalities, and maintain safe operation. Safety is not dependent on a single component. It results from multiple overlapping layers of protection working together. At this point, many people begin asking an important question. If hydrogen compressors are so essential, why are they so expensive? The answer becomes obvious once we examine the engineering requirements. These machines are not simple industrial devices. They must survive extreme pressures approaching 700 bar. They must manage heat effectively. They must prevent leaks from the smallest molecule in existence. They must resist embrittlement and material degradation. They must maintain performance over years of operation while meeting stringent safety standards. The materials alone contribute significantly to cost. Specialized alloys capable of resisting hydrogen damage are often more expensive than conventional materials. Precision machining increases manufacturing complexity. Advanced sealing systems require careful engineering. Pressure vessels must withstand extraordinary operating conditions. Every component undergoes rigorous quality control procedures. Extensive testing validates performance, reliability, and safety before equipment enters service. Hydrogen certification adds another layer of complexity. Manufacturers must demonstrate compliance with demanding industry standards and regulatory requirements. Testing programs verify pressure performance, leak resistance, durability, and operational safety. Documentation, inspection, and certification processes require significant resources. While these requirements increase cost, they also provide confidence that the equipment can operate safely in real-world environments. When viewed from this perspective, the cost of a hydrogen compressor becomes easier to understand. The machine is not expensive because it is complicated for the sake of being complicated. It is expensive because it must perform a difficult job safely, reliably, and efficiently. Every dollar invested in materials, engineering, testing, and certification contributes to a machine capable of operating under some of the most demanding conditions found in modern energy infrastructure. The most important realization occurs when we step back and examine the broader hydrogen ecosystem. Suddenly, the compressor appears everywhere. Hydrogen production depends on compression. Storage depends on compression. Refueling depends on compression. Transportation depends on compression. Industrial applications depend on compression. Even future hydrogen-powered ships, aircraft, and power generation systems rely on compression somewhere within the value chain. At the center of this ecosystem sits the compressor. On one side are electrolyzers producing hydrogen from water. On another side are storage systems preserving hydrogen until it is needed. Refueling stations deliver hydrogen to vehicles. Transportation systems move hydrogen across regions and countries. Industrial facilities consume hydrogen as a feedstock or energy source. Power generation systems use hydrogen to support energy reliability and decarbonization efforts. Connecting all of these elements together is the process of compression. This is why the hydrogen compressor represents much more than a single piece of equipment. It represents a hidden enabling technology that supports an entire energy system. Most people never see it. Most people never think about it. Yet nearly every hydrogen pathway depends on its existence. Compression transforms hydrogen from a difficult-to-store gas into a practical energy carrier capable of supporting transportation, industry, energy storage, and future clean energy infrastructure. The lesson extends beyond hydrogen itself. Throughout history, civilization has relied on hidden systems that receive little public attention. Power transformers make electricity possible. Pumps make water systems possible. Compressors make modern hydrogen infrastructure possible. These machines operate quietly in the background while enabling visible technologies that attract headlines and public interest. The hydrogen compressor is one of those hidden machines. It sits behind the storage tanks. It sits behind the fueling stations. It sits behind the trucks, ships, aircraft, and industrial facilities that may one day define the hydrogen economy. Understanding hydrogen therefore requires understanding compression. When you understand the compressor, you begin to see the invisible infrastructure supporting the future of energy. And that may be the most fascinating part of the entire story. The future of hydrogen is not determined solely by production technologies or fuel cell vehicles. It is also determined by the hidden systems that store, move, compress, and deliver hydrogen safely and efficiently. The compressor may not receive the attention of an electrolyzer or a hydrogen truck, but without it, neither would fulfill their purpose. It is the machine nobody notices, yet it remains one of the most important machines in the entire hydrogen economy. If you want to continue exploring the hidden infrastructure behind hydrogen, from electrolyzers and compression systems to storage, transportation, refueling, industry, and power generation, visit H2 Hub by Renee Energy. There you can explore the engineering, economics, and real-world systems that make hydrogen possible. Because the more you investigate these hidden systems, the more you realize that the future of hydrogen depends on far more than production alone. It depends on the invisible machinery of civilization working quietly behind the scenes every single day.